So in this video, we're going to start talking through some statistics, some summary statistics, and then later on we're going to look at some Excel and sort of see what we can do there with just some very basic features. Now, statistics are everywhere, okay? So statistics are all around us, whether they be in the newspapers, whether they be used by governments to put particular policy in place. But I kind of argue that the vast majority of people don't really know how to interpret statistics properly. A lot of people think they do, and I think it is a pride thing. You know, admitting that you don't know something or admitting that you don't know how to do something, that takes a lot. And therefore pride kind of takes over, and so as a result people pretend that they know how to do something. And I see this a lot with regards to statistics. I by no means am an expert when it comes to statistics, but I at least have the capability to turn around and say, well, I don't really understand this yet, so I need more information before I can sort of make a decision. Whereas I think a lot of people just see statistics, and because they see statistics everywhere, whether it be in the newspaper, whether it be thrown out by government, they're almost lulled into a false sense of security, and they think that they understand what these statistics mean, when actually they don't. They don't really know how to interpret these statistics successfully. So what I'm going to do over sort of the next few minutes is hopefully highlight some of the examples of the ways which statistics can be misused, and hopefully that will give you the kind of humility to go away and educate yourself on how you should be interpreting statistics, okay? And how you should be kind of thinking about statistics when they're thrown out there, whether it be by media or whether it be by the government. And actually, if you want sort of a starting place, this is quite a good article to look at. So this was written by Carlo Rovelli, who is a physicist. He's written many, many books, fantastic science communicator. And he basically wrote for The Guardian this particular article, which highlighted the fact that actually statistical literacy isn't just a niche problem. During a pandemic, it can actually be fatal. So at the time of recording this video, we are in the middle of the coronavirus. And a lot of the decisions which are being made with how to deal with the coronavirus, whether it be through social distancing, wearing a mask, whether it be washing your hands or asking people to self-isolate, a lot of these decisions are based on statistics. And if people don't really know how to interpret these statistics, I would argue they don't really have the evidence in front of them. So as a result, they're just being blindly told what to do, but they're not able to interpret for themselves and not able to think for themselves. And I think particularly during a pandemic, that can cause death. You know, when it's a case of life and death, it can be fatal, okay? So let me give you a few examples of the way which statistics can be misconstrued. So first of all, I'm going to start off with this quote that was written by Nate Silver, who wrote The Signal and the Noise. And I'm just going to throw this quote out there, and I'm not really going to talk through it at all. And I just want this to kind of settle in. And then over the next few slides, I'm hoping that this will sort of bring its own meaning to you. Like, what does it mean to you? And it says, the numbers have no way of speaking for themselves. We speak for them, and we're the ones that imbue them with meaning. So just pause the video for a second, just let that kind of sink in. Just think, what do I think that means? Then hopefully over the next few slides, you'll kind of be able to think a little bit more and just sort of realize exactly what this means as well. So let's start with an example then. This is a real life example of an advert that was run in 2011 on the London Underground. And just to give you a little bit of context, in 2011, a young man called Mark Duggan was shot dead by the Metropolitan Police Service Firearms Division, SCO 19. And as a result of this shooting, there went on to be many, many riots right across the country. Majority of them in London, but they're also in cities such as Manchester. And people were basically asked, because the face of these riots, it does seem to be that young people were the ones that were doing these riots. And afterwards, people were asked, they were given a survey, and they said, how many young people do you think, on average, commit youth violence? And worryingly, 40% of people that were asked said that they believed young people were these violent criminals. And they believed that when they walked down the street, they saw young people as young violent criminals and this kind of stain on society. And so as a result, this advert was put out there by the London Underground, which was 99%. And the argument was that 99% of young Londoners do not commit serious youth violence. Now, the reason why I picked this advert out in particular is because it's put from the perspective of a very important point of view. We call this positive framing. Like 99% of young Londoners not committing serious youth violence, that's a good thing, that's a positive thing. So therefore it's framed from a positive point of view. However, it's very easy to interpret this from a negative point of view. Exactly the same statistics, so I'm not changing the numbers at all, I'm not lying, I'm using exactly the same statistics, but I'm just looking at it from a negative point of view. So the positive framing would be 99% of young Londoners do not commit serious youth violence. The negative framing would be 1% of young Londoners do commit serious youth violence. Now, admittedly, this in itself doesn't sound that scary, but I can manipulate this further if I want to. Because if I take that in 2011, there were 1 million young Londoners living in London, then if I look at the positive framing, that means that 990,000 there were 990,000 young non-violent people living in London. In other words, there were 990,000 people who weren't violent that were living in London and who were young. But if I look at it from the perspective of the negative framing, that leaves 10,000 of people who were violent and living in London. So I'm literally just using the 99%, the 1%, and looking at the total number of young Londoners living in London to get a raw figure. Now, the reason why I wanted to highlight this is because if I put this on the front of a newspaper, let's suppose I want to put it from a negative framing. If I put this on the front of a newspaper, this would probably be a reaction. Like, who cares? 1% doesn't sound that bad. It leaves 99% of young people who aren't violent. That's a good thing. Right? That's a positive thing. But if I put this on the front of a newspaper, it's still negative framing, it's still exactly the same statistic, I've just given it in a different form, suddenly this is probably going to be your reaction, because 10,000 sounds like a lot of people, right? So again, just be aware that even though all of the statistics I've given you are absolutely factually correct, they've been put across from a particular point of view. So again, it's about understanding what they mean and being able to put them in the context of the situation which you're dealing with. Another example of where statistics was seen recently, you may be familiar with the Brexit campaign. So Brexit is basically the campaign for the UK to leave the European Union. And it took place in 2016. And there was the Leave campaign and there was the Remain campaign. Now, this particular slogan was very, very famous. It was on the side of a bus and it was by the Leave campaign. And it was designed in a particular way to encourage people to kind of vote to leave the EU. They wanted that to happen for the Vote Leave campaign. And you can see that the slogan said, "We send the EU £350 million every single week. Let's fund our NHS instead." Now, if you're not familiar with what the NHS is, it's the National Health Service. It basically entitles every UK citizen to free healthcare. Okay, and it basically means that the citizens of the UK will be looked after, at least from a health perspective. Now you can see what the Vote Leave campaign was trying to do here. They tried to put the £350 million, which is a very big number, like £350 million, I'm not arguing, is a very, very big number to put on the side of a bus, particularly for an individual, and NHS together. Look how close they are together. So this has been very deliberately manipulated to kind of try and tug on people's heartstrings. The idea is you put a big number on the side of a bus and you sort of suggest that actually this could be used for the NHS, this kind of national treasure, which people kind of really support and really want, okay? Putting the two things together, what do you think people are going to do? However, I always ask my students, can you make this number small? What does this £350 million actually mean? Because from an individual level, like if I said, oh, I had £350 million, that'd be a huge, massive amount of money. But we're not talking from an individual level, are we? We're talking from the level of the UK, okay? Because this is how much the £350 million a week, this is how much we send the UK, how much we send the EU from the UK. So it's, if you like, a national figure. So actually, how big is that? Well, one of the ways that we can get a feeling of that is what it would mean if we scaled it down to be an individual level. So instead of looking at it from a national level, from the UK level, what would it actually mean from an individual level, an individual perspective? So if we take the fact that there are about 66 million people living in the UK, at least at the time of the 2016 referendum, if we take that £350 million, divide it by 66 million, it would equate to about £5.30 per person per week. Suddenly, that doesn't seem as big. So all I'm literally doing here is putting this number in perspective. If this number is talking about a nationwide level, a UK level, what would it mean from an individual level? And suddenly £5.30 doesn't sound a lot. In fact, I could scale it down even more by scaling it down to saying, well, if this is per week, what if we were talking per day? Well, if we divide that by 7, we basically get about 76 pence a day, which is about the equivalent of a packet of crisps. So if suddenly you change the slogan on the side of a bus to be what it actually means from an individual level, again, this statistic is totally correct, except it's not, because it didn't actually send £350 million a week. That was the pre-rebate figure, where you actually send more like 200-ish million pounds. But never mind, let's suppose that was correct. If we suddenly change it to what it means from an individual level, if we said we send the EU a packet of crisps every single day, let's fund our NHS instead, again, does that really have the same meaning? So again, it's just about how you interpret those statistics. What do those statistics actually mean, okay? Now, another example of where statistics is commonly misinterpreted in everyday life. This is a real life example by the Daily Express, which is a national newspaper in the UK. And it says that a daily fry-up boosts cancer risk by 20%. Now, if you don't know what a daily fry-up is, it's basically a breakfast with like bacon and eggs and sausages and beans and I think black pudding and mushrooms. It's not considered a very healthy breakfast. It's very high in fat and it's typically not very good for you. And basically what they were arguing is that if you have one of these unhealthy breakfasts every single day, it boosts the chance of you getting pancreatic cancer by about 20%. Now again, this sounds scary, right? And hopefully the idea is that people look at this and go, if I have a daily fry-up every single day, I have more chance of getting cancer and I have an increased risk of 20%. They see that 20% and they think, okay. But my argument is, what does that 20% actually mean? Can you actually understand what this 20% actually means? And can you put it in context for me? Well, what you're talking about here is something called relative risk, okay? So if you boost your risk of getting cancer by 20%, what they're actually talking about there is something called relative risk. And basically what that does, if you put two kind of sets of people and you compare these two sets of people, one that has a daily fry-up every single day, one that does not, and if you compare the chance of whether they have cancer or not, you have a 20% increased chance of getting cancer if you eat a daily fry-up every single day. So the group that has that daily fry-up every single day, they have a 20% increased risk over those people that don't have the daily fry-up. So you're just simply comparing the two groups. And the way that you find that relative risk is just by dividing the new risk by the old risk. So in other words, the new risk are the people that eat that daily fry-up every single day. The old risk are the people that don't have that daily fry-up every single day. So you look at the risk of each group getting cancer. Okay. Now, there is another type of risk, and it's something called absolute risk. Now, absolute risk kind of deals more with actual figures, and the way in which you calculate it is instead of dividing the risks of getting cancer for these two groups, you should subtract the risk of getting cancer for the two groups. So just remember, you have two groups in a room, one that has a daily fry-up, one that doesn't. You look at the risk of each group getting cancer. For relative risk, you just divide those two risks. And for the absolute risk, you just subtract the two risks. So you subtract the two groups, okay? So what is absolute risk actually getting at? Because at the moment, 20%, this thing on the front of the newspaper, is talking about relative risk. In other words, they're just dividing the risk of getting cancer for the two groups by each other. But what is absolute risk? How can I interpret this? So I know, because I've gone on the Cancer Research UK website, that about 1 in 80 people will get pancreatic cancer in their lifetime, regardless of whether they eat daily fry-up every single day. Just the risk of getting pancreatic cancer is about 1 in 80. So what that literally means, if you want to interpret that 1 in 80 figure, is that if you put 400 people who do not have a daily fry-up in a room, so here's my 400 people on the screen who do not have a daily fry-up every single day, if you put them in a room, well, you'd expect 5 of them to get pancreatic cancer anyway, just by pure chance. That's what the risk 1 in 80 means. So let's suppose these 5 poor souls get pancreatic cancer just by pure chance, okay? So now, if you go back to the website, or you go back to the front page of the newspaper, it says that the increased relative risk is 20%. In other words, 20% means 1 in every 5, yeah? 20%, 1 over 5, or 1 in every 5 people. So what that means is that if you now change these people, because this is the risk of people who do not have a daily fry-up every single day. If you change these people to the people who do have a daily fry-up every single day, well, you should still have these 5 people just getting cancer by pure chance. It's just that now, because you're having a daily fry-up every single day, you expect that 20% more will have pancreatic cancer instead. That's what the 1 in 5 people mean. So there's an increase of 1 person who will now get pancreatic cancer compared to the group of people that before. So in other words, it's gone from 5 people who just get cancer by pure chance to 6 people, okay, just by eating that daily fry up every single day. Okay, so you've just got to think, well, okay, if you go there then, it's just an increase by 1, and 1 in every 400 is about 0.25%. That is your absolute risk, okay? So the absolute risk is basically looking at the difference between the people who don't have a daily fry up every single day and the people that do have a daily fry up every single day, and you will see a difference in the people that get daily pancreatic cancer of 5 to 6, so the difference is 1 person. So basically 1 person extra, that's all you're going to have. So if you look at 1 in every 400, that's going to give you 0.25% absolute risk, okay? So you can kind of see, well, which one is going to give you a more kind of, it's going to sell more papers, okay? Which one's going to put this, is going to put this on the front of the newspaper? Is it going to be the 20% increased risk or the 0.25% increased risk? Well, I would argue the relative risk statement would be more inclined to sell papers. It's going to capture people's attention more. Now, again, I have not manipulated these figures at all, okay? All I have literally done is used exactly the same statistics, but I've just used them in different ways. And being a statistician, you need to be aware of all of these different ways in order to make an informed decision. So all I'm trying to say to you is, just because you see a number, don't believe that that number is the be all and end all. Sometimes that number is not telling the full story, and your responsibility as a statistician, as really a member of any kind of well-regarded society, is to actually understand what these statistics mean. So just be aware of that the next time you pick up a newspaper and you see a kind of statistic and you think, okay, just make sure you understand what that statistic means. Now, some more examples. This is not just a one-off, okay? Some more examples of where statistics, this sort of idea of absolute versus relative risk can be found. If you look at this statement on the front of the Independent newspaper, so a different newspaper this time, summer-born children are more likely to be diagnosed with depression than older pupils. Well, if you look at the relative risk, that's 30%. That's a massive number, right? But the absolute risk is only 0.2%. If you look at another example from CNN Health, daytime naps once or twice a week may be linked to a healthy heart, researchers say. Well, relative risk 48%, but absolute risk only 2.8%. Okay, so again, you just need to be aware of all these different risks. And if you look at this one by the Daily Mail, hidden fat raises a woman's risk of type 2 diabetes and heart disease with every extra 2.2 pounds boosting her odds by 7-fold. Again, look at the relative risk, that's 650%, that's massive. But the absolute risk is only 5%, okay? So just because you see these numbers on the front of newspapers, just be aware, what do they actually mean? You need to have the ability to be able to go away and be a little bit of a skeptical and be able to interpret these properly. So don't just treat them on face value. So let's just talk through then the real job of a statistician, okay? So really what statisticians are trying to do is they're trying to make decisions based on evidence. And just to kind of really summarize everything which statistics is all about, I've tried to do this on this slide here. So let's suppose your grandmother makes this really beautiful looking cake. And I mean, it looks absolutely divine. I mean, it's chocolate, it's got cream on, it's got the strawberries on the top. It looks delicious, right? Now, my question to you is, do you need to eat this entire cake in order to work out whether this is delicious or not? And the answer to that question is no. No, you do not need to eat the entire cake. What you need to do instead is just eat a sample, okay? So you just need to eat a little slice of cake and then you'll be able to determine whether the rest of the cake is delicious or not. Okay, so this is getting into the idea of a population versus a sample. So in other words, the entire cake would represent a population. That's the entire group which you're interested in. Now, it could be every single person in the college. It could be every single person living in the UK. It could be every single person living in the world. It may even be every fish. It may even be every type of ball in a particular bag, okay? So a population is the entire group of interest, whereas a sample is just a selection, okay? It's just a subset of the population. So in this case, if I ask the question, is this cake yummy? Is this big cake which you've made yummy? You don't need to eat the entire cake in order to answer that question. You just need to take a sample. You just need to take a little slice of cake, taste that, and then you'll be able to infer what that means at the population level. So we call this an inference. The idea of an inference is if you can understand something about the sample, you can then understand something about the population. So the idea is that something in the sample will tell you something about the population, okay? And really what statistics is all about is trying to understand how to interpret sample level statistics to population level parameters, okay? So if we're working with a characteristic of a sample, for example, we might be working with the weight of the cake, or we might be working with the height of a cake, or we might be working with particular kind of characteristics or measures that we want to look at, we would call this a statistic. Okay, so just think sample, statistic, it begins with S. Whereas if we're looking at a population, if we're trying to measure a population and understand things about the population, we call that the parameter. So basically, if we take a sample, if we take a subset of the population and we try and measure something, or we try and look at a characteristic, it could be weight, it could be height, okay, it could be color, right? We would call that a statistic because we're looking at the sample. Whereas if we're looking at the entire population, we call that a parameter. So again, if we're looking at measures of the population, we call that a parameter. So there's kind of few key words on the screen there: statistic, sample, and parameter corresponds to the population. And hopefully you understand the whole point of statistics is if we can understand something about the sample level, that should then be able to infer something about what's happening at the population level. Now, if you're interested, I have actually put other videos on my slide where I continue working through these on my website, on my YouTube channel, and I've continued working through these slides. It's theme 1 of advanced statistics, okay? So please feel free to go away and have a look at that, and then we can talk about the different ways in which we get a sample out, and also talking about how we can measure populations as well through censuses and stuff like that. But in the meantime, just for the sake of this particular module, I want to talk you through 2 really key ways of summarizing data. Okay, so we've talked about the way in which data can be used and perhaps can be misinterpreted sometimes. Now we're actually going to talk through some of the ways in which we can actually look at data, and then we can make some summary statistics based on that data. Okay, now the first type is a measure of central tendency. Okay, so as an example, let's have a look at through these kind of particular things here, okay? So let's suppose I just want to look at a set of data, and perhaps I might have some graphs and things over here on the right hand side, and I want to just produce a single value that best represents that particular data set. So if I'm just looking at a single value, I'm just taking a data set, and I don't want to tell you all of the individual data, all of the individual numbers. I just want to come up with one number that represents that data set. It's almost like the prime minister of a country. It kind of goes forward and represents the entire data set. We call that an average. So an average is something that represents the entire data set. It's just a single number. And there are 3 types, okay? You've got the mean, you've got the median, and you've got the mode, okay? Now, it just so happens that the mean, the median, the mode usually happens somewhere in the middle of the data. So it's usually that the data, the way the data is presented, we usually pick out a value which is somewhere in the middle. And that kind of makes sense because you don't want to pick out a number which is really small, you don't want to pick out a number which is really big, because there's probably going to be outliers in the data as well. And they're usually going to occur at the extremes. So the average, the kind of single number that best represents the data, is usually in the middle. So we call that the measure of central tendency. It's literally where the center of the data tends towards. And there's 3 types. There's the mean, the median, and the mode. So do not get confused with the fact that you think average just means mean. It doesn't. It means a mean, a median, or a mode. And there are different situations over when you should use each type. Okay. So I'm going to talk you through very quickly the different types of central tendency we can have. So the most common value in the data set we call the mode. So the mode is basically the value that comes up the most often. So as an example, if I look at this first data set here, so 3, 5, 8, 5 and 2, maybe you might want to pause the video and think, which value comes up the most? Which is the mode? So hopefully you've had a chance to pause the video, okay? And you look at this data set and you think, okay, well, which value comes up the most? Well, can you see it's the 5? Because the 5 comes up twice, okay? So for this particular data set, the mode is 5, okay? If I look at data set B, I have 13, 62, 13, 13, 25 and 60. The mode would be 13 because 13 is the number that comes up most often. If I look at data set C, so 1, 5, 2, 8, 2, 1 and 9, can you see that in this case there are actually two modes? There's 2 because 2 comes up twice, but there's also 1 because 1 comes up twice as well. So if you have a data set with 2 modes, you call that bimodal. So bi meaning 2 and then obviously modal meaning mode, okay? So if you have 2 modes in a data set, you call that bimodal, and that's totally fine. Okay, so just note that the data set doesn't need to be ordered, so you don't need to put these numbers in order of size from smallest to biggest or biggest to smallest in order to find the mode. Okay, it's just simply the most common. If I look at median, well, median is simply the middle value. Okay, so in other words, if you put this data set in order from smallest to largest or largest to smallest, just as long as it's an order of size, and if you walk along this data set and stop when you get to the middle value will be the median. Okay, so as an example, the median in this case would be 3. For data set B, the median will be 55, and for data set C, the median will be 43. So in this case, you do need to order the data set in order to find the median. Finally then, the mean is basically asking, well, if all of these numbers were the same, what would that value be? So basically, if I look at this data set here, so 4, 6 and 2, and if I just suppose that all of these numbers were the same, what would that number be? Well, first of all, the way which I do that is I say, well, look, I have 3 values, okay? If I add all these values together, so 4 plus 6 plus 2, I get 12. So let's just suppose I didn't know that I had 4, 6 and 2 in my data set. If I told you 2 things, if I told you that all the values in my data set added up to 12 and there are 3 numbers in my data set, what would you say that number would be? Well, the mean basically says if the numbers were the same. So what would that number be if the numbers were the same? So if they add up to 12 and there's 3 numbers in my data set, I would argue that it would be 12 divided by 3, which is 4. Right? If I say that all the numbers were the same, if it was 4, well, 4 plus 4 plus 4 gives me 12. So I would say that the mean in that case would be 4. If I looked at the next data set, I had 10 plus 52 plus 38 plus 60. Added those together, see what I got, divided it by 4 and said, well, if they're all the same, then the mean would be whatever those things added together divided by the number of data points I have, okay? So the way which I work out the mean is by adding all the data points together and then dividing by the number of data points that I have. Now, one of the ways that I can actually see where the mode, the median and the mean would lie is by looking at something called a histogram. Now, a histogram is effectively a way of ordering the data. So I put the data in order from smallest to largest, and then I just simply draw how many things are in each bar. So I basically group the data into particular groups, and I put them in groups from smallest to biggest, and I basically just draw how many things are in each bar. Okay, and that's a histogram. It's an idea of size. So you can see the majority of my data would be clustered in the middle here, so be clustered around the middle. Okay, so basically the idea is the area of the histogram should give you an indication of how many things, and it should give you an idea of the distribution of the histogram. So if I want to find the mode, quite simply, it's just going to be the one with the highest bar. Okay, that's going to be my mode, right? So it's the most common value, so therefore it's the highest peak of my histogram. If I look at median, well, the median is the one halfway in the middle, and if frequency is given by the area, all I simply need to do is divide the area in 2. The point halfway down the middle of those 2 areas would be where my median is. The mean, however, a bit like the balance point of a histogram. Okay, so imagine this is almost like a seesaw. The mean would be sort of roughly about here. Now, interestingly enough, the mean is always attracted towards outliers. It's influenced by extreme values. Let me show you why. So if I come to this particular website here, so this is my GeoGebra page, okay, and if I open this GeoGebra page up, so I get something that looks like this. Now in this circle here, I basically have loads and loads of circles. So if I show you, in this circle here, I basically have loads and loads of circles. And the idea is that each one of these circles represents a data point that I can drag and put over here on the right-hand side. So you can see over here, basically, I'm starting to build a histogram. So let's suppose that data point is 2. Let's suppose I have another data point of 2, so I can stack it, so I get a more increased bar. Let's suppose I put another data point sort of to the left at 1, and another data point over here at 3. Okay, so I get a nice little histogram appearing over here. And you can basically see with this particular histogram, I have the median, the mean, and the mode. They're all the same. So they're being represented by the different arrows. And you can also see the mean, the median, and the mode over here. Okay, I can even have something like a bimodal data set. So something like that, where I actually end up having 2 modes. So you can see 2 green arrows, but you can see the mean and the median are roughly in the middle again. So that's the reason why they're called central tendency, because they're always roughly in the middle of my histogram, okay? But if now I grab another data point and I put it way out towards the right, Do you notice that the median and the mode kind of stay relatively median and the mode stay relatively fixed? Okay, they're not really influenced. But look what's happening to the mean. The mean is almost like being attracted towards this outlier. So again, if I drag this data point way out over here on the right, can you see that the mean is almost like a magnet? It's being attracted towards that data point. So in other words, the median and the mode are relatively reliable and stable measures of central tendency. The mean is also reliable as long as you don't have outliers in your data. So the mean will always be influenced by outliers in your data. Okay? And as a general rule of thumb, I would always encourage you to use median. There are particular situations over when you should use each type, so the mean, the median and the mode. But if you're not sure, the median is generally the most stable and most reliable. Now, just to finish off central tendency here then, I just need to make you aware of some different types of variables which you can have. So first things first, variables are generally grouped into two categories. You can either have quantitative or qualitative. Now, another word for those, which I've written on the screen, are either numerical or categorical. Okay, so quantitative means a quantity, it means a number, hence they're called numerical. Qualitative is more about describing qualities, and they're usually to do with text information, and we usually put those into categories. They're called categorical variables, okay? So, if you're dealing with a numerical or a quantitative variable, it's usually a data that represents counts or measurements. It's data that results in numbers. So examples might be age or height or length. Whereas if you're dealing with a categorical or qualitative variable, it's data that represents groupings or categories, hence the categorical part, okay? So it's data that can be put into groups, okay? So such as gender or eye colour. Now you can actually subdivide each of these two variables further. So if you subdivide a numerical variable, you can put it into interval or a ratio variable. So an interval variable is data that will result in a meaningful interval or range of values. So as an example, what is your body temperature? That can result in a range of values, usually somewhere around 37 degrees, but it can result in like 36, right the way up to 40 degrees if necessary. Okay, so again, it can result in meaningful interval or range of values. Now, ratio variable is very subtly different, okay? So it still can result in a meaningful range or interval of values. However, if you have 0, it means that the variable doesn't exist. So with an interval variable, 0 is allowed, okay? So zero is technically a valid count or measurement that you can have for an interval variable. Whereas with a ratio variable, if you get a 0, it means that that variable does not exist. That value does not exist at that point, okay? So for example, if I ask you, how tall are you? Well, if you have a height of 0, it means you do not exist, okay? Because there's nothing there. Same with how old are you? If you have an age of 0, it means that you haven't been born or you don't have an age, right? Now, if I break down categorical variables, again, I can break that down into nominal or ordinal variables. Now, the clue's kind of in the name, so just remember, categorical variable is kind of data that results in groupings or categories. It's kind of textual information. If I talk about nominal, nom kind of means name. Okay? If I say the word nom to you, it means name. Nombre, for example, in Spanish means name, okay, or nom in French means name. So nominal means a named value. Okay, so it's data that can be identified by categories, but this is the really crucial bit. It doesn't necessarily mean that they can be put into any natural order. For example, if I asked you, what gender are you? Well, okay, you can put yourself into specific categories. You can put yourself in male, female, or other, but there's not really any order there. Like, I can't really order males above females above other. Like, equally, I could have gone females, then males, then other. So there's not really any order that you can have there, okay? Whereas if I deal with ordinal variables, guess what? The clue is in the name. It has to have an order associated with it. So ordinal order, right? So it's data which can be put into categories, which can be ordered in some way. So as an example, do you like statistics? You can order that from not at all through to somewhat, through to very much. So again, there's a natural order there, not at all, right the way through to very much. There is some kind of natural order that you can have there, okay? So if I ask then when you can use each type of central tendency, so if you want to use mean, median or mode, as a general rule of thumb, you should kind of think of this table over when you should use each measure, each type of average. So if you're dealing with nominal variables, just remember nominal variables are numerical, okay, so they can result in nominal variables are categorical, so they can result in groupings or categories, okay, and nominal just means that they're named. There's no particular order associated with them. So therefore, because there's no particular order, there's no point dealing with median, because median says that you have to order the values, and also it doesn't really make sense to use mean there either, because there's not really going to be any values which you can put there, okay, there's not really going to be any values that you can code there. So therefore, I think mode, it's just simply which category has the most things in them. That's going to make sense for nominal variables, okay? If I'm going to deal with ordinal variables, well, again, you know, which category has the most things in, I think mode will be allowed, but I think also we can have median as well, because again, I can put the categories into order, which means that I can take the median, okay? If I put them in order, look for the middle value, I can take the median. So I think mode or median, those will be valid for ordinal variables. Now the next type of variables we'll be dealing with numerical, and I just need to think about the different types. So if I have a nice symmetrical data set, in other words it's nice and even, okay, there's no particular outliers or no particular kind of outliers that are skewing the data in one way, then I think we can use any of these three. These will all be fine, because actually they should all be roughly the same in symmetrical data set anyway. Whereas if I'm dealing with skewed data set, in other words, I have one particular outlier that kind of skews the mean one particular way, well, again, you may be able to use mode and median, but then I think it invalidates the use of the mean, because you just saw in kind of that activity where we're dragging and dropping, the mean will always be attracted towards any outliers which you have in the data. Okay, so in that case, I think the median would be fine. You could use the mode as well, but to be honest with you, I think median would be fine. Okay, so you can just stick with median if you wish. So if you're ever not sure about which one to use, you can see that median wouldn't be a bad bet, because it can basically be used for all three of these types of variables. It just can't be used for nominal because you can't obviously order them. Okay, so either median, mode could be fine, but I would actually stick with median, particularly if you're dealing with numerical variables. Okay. So yeah, as a general rule of thumb, if you want to deal with categorical variables, use the mode. If you want to deal with numerical variables, use the median, and you can't go far wrong with that. So just to kind of illustrate this and just to kind of finish this little section off, if I kind of ask these 4 questions, perhaps you might want to pause the screen and just kind of have a look at these for a quick kind of couple of minutes or so. They're literally just kind of questions, you know, I've deliberately been ambiguous by saying average. I want you to think in each case, what would the mean be? What would the median be? And what would the mode be? And then in which case, which would be the kind of correct kind of measure of central tendency? So just to go through these very quickly then, what's the average number of legs? Well, if you think, most people will have 2 legs. So in that case, I would expect the mode to be 2. The median would basically say, if I'm going to put these people in order, so in order from no legs, right the way up through 1 leg, right the way up to the people having 2 legs, so I'm literally putting them in order of the number of legs which they have. I walk along that line and I stop when I get to the middle person. How many legs would I expect that person to have? Well, I would argue that actually the median in that case should be 2, because most people do have 2 legs, right? Whereas the mean, if you think about it, the mean is always skewed towards outliers. So because there are some people with 1 leg and even some people with 0 legs, those are the kind of outliers. You expect most people to have 2 legs, but there's still some people with 1 and 0 legs. So in which case then, the mean will be skewed to something less than 2, okay? Something like 1.9-ish, okay? So this is what I would expect the mean, the median, the mode to be in that case. If I'm talking about average number of testicles, well, again, I think in this case, mode is going to be either 0 or 2, because if you're a female, you have no testicles. If you're a male, most males have 2 testicles. But there are also some males with 1 testicle as well. But I would argue the mode, it would be bimodal, it would be either 0 or 2. Okay, if you're dealing with median, well, that's something slightly more tricky to deal with, because again, just imagine you order all the people that you have in order of the number of testicles, right the way from 0 through 1 testicle, right the way up to 2 testicles. Again, you walk along the line, you stop in the middle. Now, if you think about it, there's roughly 50% females, roughly 50% males in the world. And in fact, I think it's not. It's slightly balanced in favour of females. But if you imagine they're about half and half male and females. If you walk along that line, you get to the halfway point, you expect that halfway point to be either 1 or 0, okay? Because you expect that actually there's going to be all the males with 1 testicle before you get to the males with 2 testicles. Right? Does that make sense? Because if there's half females, half males, then half of those, or half of the line should be consisting of males, but you should start with the males that have 1 testicle. So actually you should be between 0 testicle and 1 testicle, okay? So that's the median, whereas the mean will actually be skewed in favour of the outliers. So I think actually the mean will be slightly less than 2. So here we go. So it'd be a bit less than 1 for the mean. The median will be 1 because, again, you're walking along that line, you get to the halfway point and you walk up to the person who has either 1 testicle, okay? And then the mode would be either 0 or 2. If you talk about the average number of sexual partners then, well, okay, the median and the mode should be roughly around 5. I think that's kind of the average. Whereas there's some people out there who slept with hundreds, if not thousands of people. So therefore, the mean will be skewed again in favour of those people, so it'd be much higher. Okay, and if I again talk about the average income, similar kind of idea, median and mode should be around 30,000, but there's some millionaires and billionaires on the planet which will skew the mean well above 50,000. Okay, so finally then, let's look at another summary which is really useful, because mean, median and mode, averages, measure of central tendency, they're really good, okay, and they're really good at just getting one number across that kind of gives you an idea of saying, if I take an average person, of course it's up to you what you mean by an average person, but on average the mean, the median, the mode will give you an indication of what you expect from this particular data set. Now, measures of variation, as the clue in the name kind of suggests, means how do things vary, okay? So how do things spread out? How do things change? And in fact, to illustrate this, I think we're going to have a look at this in Excel. So you can see here that I've opened up an Excel spreadsheet, okay? Now, there's a really important thing which I need to put across here. Some people out there absolutely love and swear by Excel, and that's fine. But you have to be aware of its limitations, okay? As with anything, as a data scientist or as somebody who works with data a lot, you need to be aware of the limitations which certain applications have, okay? So some people out there that absolutely swear by Excel and wouldn't use anything else for their data analysis. I'm not in that category because I personally think Excel is fine for kind of doing very basic summary statistics where data isn't actually that important. But if you're dealing with really important and vital data, you should not be using Excel at all. You should be using other programs, okay? And it's basically the idea of a difference between a spreadsheet and a database. So a spreadsheet is basically what Excel is, okay? You've basically got loads and loads of cells, okay? So things which I'm highlighting now, these are all cells and they're all kind of independent. Now, sure, you can reference one cell in terms of another cell. So as an example, if I put 2 in this cell and 5 in this cell, or 4 in this cell, then I can basically add these two things together. So that plus that, okay? So basically whatever goes in this cell here, will basically be a sum of whatever's in this cell and this cell. So sure, I can kind of reference one cell in terms of other cells, but nonetheless, they are all independent. Also, I can kind of change things with Excel, such as I can say, for example, I want everything in that cell to be a percentage. But the trouble is with this, if I want to type text in this cell, I'm still allowed to do that, okay? Because each cell is kind of independent. So even though I make put kind of some kind of condition where I say, I would like this to be a percentage, if I go and type textual information in there, it would still allow me to do that. Whereas a database, it won't allow me to do the very thing that I've just illustrated. So if I want a percentage in this column here, for example, it may be talking about a test score, okay, and I need a percentage there, it means that if the next column is expecting textual information, I can't mistakenly type information in one cell where it's not expected. So in other words, I can't easily make mistakes with a database, okay, but I can easily make mistakes when I'm putting data into a spreadsheet. So that's one reason why you shouldn't use Excel, okay? Another reason of why you shouldn't use Excel is because, and actually this is a real life example, is because you need to understand the limitations. Excel is incredibly powerful, and I have made Excel do really quite amazing things which I never thought Excel could do. And it is a very powerful software. However, you have to be aware of its limitations, and it is very easy to abuse it. It can be very easy to think, oh, well, Excel is very simple and easy to use. I'm just going to use Excel to do everything. Well, unless you know about its limitations and where things aren't going to work in Excel, then you're in with an issue. An example of this was with the most recent, again, coronavirus. The government was basically storing values in Excel and basically importing values from a different format, putting them in Excel, and they didn't really understand the limitations of Excel, and as a result, you've lost data, okay, because you were abusing the way which Excel should be used. So just be aware. Excel is a very powerful software to use. It can be very helpful if you're just doing very basic summaries, but if you're really using it for analysing data, I would strongly recommend that you use something separate. In principle, the idea of good kind of data management is that you should have your data stored in a database, which the difference between a database and a spreadsheet, I will just quickly talk about this. A spreadsheet, like I say, are lots of individual unique cells. And sure, you can reference cells to other things, but ultimately they are unique cells. And as I've shown you, if I turn that cell there to be a percentage, it means I can still put like textual information and stuff like that in there, which is not necessarily what you can do in a database. With a database, if you say that column is meant for a percentage, it means you can only put a percentage in there, okay? And it means that you can't easily put data in the wrong place in a database. The other reason why you should use a database is because then you store your raw data elsewhere. So as a general rule of thumb, when you're analysing data, you store your data elsewhere, and then you analyse it in a completely separate software or program, such as SQL or R or SPSS. So in other words, you have your data stored somewhere, you can't edit that data, that's your raw data, then you use somewhere else to physically edit your data. Okay, so a lot of people make the mistake of using Excel, having your raw data in Excel, and then manipulating the data in Excel. And I'm like, what are you doing? Now, admittedly, that is fine for kind of basic stuff. Maybe you might have the data saved elsewhere, so if it does go wrong, then you can just easily call it back in. But as a general rule of thumb, just please be aware that Excel is not the be-all and end-all. Okay, anybody that tries to tell you that Excel is an amazing software, I'm always going to use Excel and nothing else, they're wrong. You need to be aware of its limitations. It's a great software to use once you're getting started. It's very accessible, but it does have a lot of limitations. And particularly when you're getting into data analysis and things like that, you really shouldn't be using Excel to analyze data, okay? Now, saying that, I know that if you're interested in becoming actuaries use Excel a lot, but they do at least have a system in place for working with Excel. So they actually analyze data in Excel. They do at least have a system in place, and it's usually through the form of a version control. So in other words, every single time they make a change to a spreadsheet, they save it as a new version. They actually have a log of what they've changed in each version. So just be really, really careful with Excel. Yes, it's great. Yes, it's accessible. Yes, I strongly recommend that you go away and have a play around with it. And I'm going to show you a little bit about what you can do today, and it can do some amazing things. It is very powerful, but please be aware of its limitations as well. If you're analyzing data in Excel, please rethink that. You shouldn't really be doing it, okay? Or at least you should have very strict measures in place to ensure that nothing can go wrong, okay? So rant over, okay? Don't think that Excel is amazing. It is very powerful, but just be aware of its limitations. It's not the be-all and end-all software, okay? So let's actually make a start then, sort of saying that. All right, so what I'm going to do is actually show you something called standard deviation, but I'm going to use Excel to illustrate it. Okay, so standard deviation is one of our measures of variation, which is measured quite a lot. It's basically the average spread from the mean. So in other words, if you take a data set and you've obviously got spread in that data set, you've got the mean, okay, so you've got the average value, you know what the average is expected to be. You've got one value, says, what value best represents a data set? That's the average. But then you want to understand, well, actually, what is the spread from the mean? Because of course there'll be a bit of variation there. That's what the standard deviation will tell you. So what I'm just going to do first of all is I'm going to generate 10 random numbers between, let's say 2 and 20. So I'm going to use the Excel function equals and then rand between. So whenever I want to use an Excel function, this is basically a predefined script that has been written into Excel. I just put an equals at the front, type my function, and then in brackets, so in this case I'm going to put my bottom and my top number, so 2 and then comma 20. If I hit enter, it's basically going to give me a random number between 15 and 20. And obviously, if I change anything here, so for example, if I go my data, it'll basically give me a new number between 2 and 20. Now I want 10. Now I could absolutely go down here and type equals rand between again. But what I'm actually just going to do is click on this cell again, and I'm going to kind of move my mouse to, you see there's a little green sort of square in the corner of this cell. So if I just come here, you can see that that cursor has changed from a big cross to kind of a little cross. So if I click on that circle and just drag it down like so, you can basically see it will generate 10 random numbers for me, all between 2 and 20. Now the issue is, if you just seen, if I keep changing things on my spreadsheet, so for example, if I put something here now, you can see that basically these numbers will all change, because every single time I change something on my spreadsheet, it will update the random number generator for me. I don't want that. So all I'm literally going to do is I'm going to highlight this column, I'm going to copy them, and then I'm going to right click on a new cell, and I'm just going to come here and I'm just going to paste the values, okay? So whatever these values were, it's going to be put here, and I can actually delete that entire column, and I'll change this to be my data, okay? So this here will be my data, and perhaps I want to plot this. Now, first things first, because I've said that I want to work out standard deviation, so let me write this definition down, okay? So standard deviation, clue is kind of in the name, so deviation tells me how things change, okay? So it's standard, so standard deviation is the average distance from the mean, okay? So I'm just going to write this down as a definition down here, and perhaps I'll merge these cells and highlight them. Okay, so merge and center, put it in the middle. Perhaps I'll change this to a nice red, make it bold, make it a little bit bigger, wrap the text as well. So that's my definition of standard deviation. So standard deviation is the average distance from the mean, and perhaps I'll put this with a yellow background to make it stand out a little bit better. So that's the thing which I'm trying to work towards. So I guess because this is my data, it's 10 data points, okay, I want to work out what the average of this data is. So I'm just going to find the mean. So by default, if I want to find the mean, it will just use average, okay, so equals average, okay, and I'll just open and close my brackets, highlight this entire column, hit enter, and that will return me the average of that particular column. Now, the way which Excel works, by the way, you notice that it's saying average. It's clearly not written by a statistician, or at least it's written by people that realize that when people say average, they actually mean the mean, okay? If you wanted median, obviously you type median there, or mode, you type mode. But you notice that it's not quite as simple now, because I need to copy this down here. It's not quite as simple as just copying and pasting all this down, because all these numbers will come out as different. Reason being is because every single time I move it down, these numbers here, so at the moment this cell here is corresponding to the range A2 to A11. So the cells are basically given a particular name. So this here would be A2, this here would be A2, this here would be A3, A4, because it's column A and row 4, okay? And this would be B2, and you can see the cell in the top left-hand corner. Okay, so in other words, I need to lock this. I need to make sure that when I drag it down, it doesn't change. So you can see by default, it's doing A3 to A12, okay, rather than A2 to A11. So in order to lock the cells, I just click here and I go F4, and it puts dollar symbols around it. And it basically says, don't change this at all when I drag it down, okay? So if I now drag this down, I get 13.4 copied all the way down. So this here is going to be my mean value. Okay, in actual fact, I'm just going to change this mean to be in red. Okay, I'll put that in red as well. Right, so this is basically the idea. I'm starting to get my data set built up. I've got my original data here, and I've got the mean of that data copied there. So I think now I'm just going to graph something. So I'm just going to highlight these two cells. I need to highlight them both. So what I'm going to do is hold down Control and highlight the second one. You can see that highlighted as separate, okay? I could highlight them all together, but then they wouldn't be separate data sets. They'd just be highlighted as the same data set. So I'm just going to highlight the first column, Control, and then highlight the second column. And now I've got two separate data sets being highlighted. Now if I go to Insert, and if I click Recommended Charts, I'm going to go to All Charts here, and I'm going to go to Combo, because I want to plot two things on here. And I'm actually going to select a line. Let's see whether I can find anything. Nothing up there. So I'm going to come down here to Series 1. So Series 1 is the first column that I highlighted, my original data. And I want that as a line chart, okay? So I'm going to go to a line chart, something like this. Okay, so line with markers. And you can see that's now changed with a line with markers. And the second data set is my average. Okay, so it's this one here, this is the 13.4. And you can see it's highlighted as the same. So it's just a straight bar, which is exactly what I want. So now if I click OK, what I basically get is a chart that looks something like this. Okay, if I make it a little bit bigger, it's a chart that looks something like this. And the idea is that the blue line, so the blue markers, is my original data, and the orange line represents that mean line. Okay, so you can kind of see that for this particular data set, the average line is the kind of point which is roughly in the middle. The kind of, as you go along here, all I'm doing is just kind of finding the line which is roughly in the middle. Again, measure of central tendency. Now I just want to change some features. I want to actually get rid of this title because I know what it's all about. So I'm just going to delete that. And I'm also going to delete the series down the bottom. Okay. And I'm actually also going to delete these numbers down here because these numbers just correspond to the value of my data. Okay. So this is my first value, second value, third value, etc. That's all that represents. I'm actually going to change the color of these as well. So I'm going to take this, I'm going to right click, and I'm going to go to outline. And I'm going to change the outline to black. So I'm going to go automatic, and again with the fill as well to make sure the markers change the same. So now you can see that is now a nice black, which is exactly corresponding to the black over here. I also want to change this sort of mean line to a dashed line that is in the same color, so it's in red. Okay, so I'm going to right click, oops, going to click it again, right click, go to outline, I'm going to change it to a nice red, and I'm also going to change the dashes to be dashed. Okay, so I'm going to change it to something like that. I may also change the thickness a little bit to maybe 1.5 pints. So there we go, so that's a little bit thinner as well. Okay, so you can basically see the mean line is a dashed line across there, and I've got my data set as a nice trend line across here as well. Okay, so far so good. I've got my data set plotted, and I've also got my mean line plotted. But now I want to actually visualize what standard deviation is doing. So standard deviation is the average distance from the mean. So what I'm going to have to do now is actually work out, well, what is the average distance from the mean? So I need to work out the distance from the mean. So I've got 18, and I need to work out how far is 18 away from 13.4. And then 17, how far is 17 away from 13.4? And how far is 14 away from 13.4? So in other words, I want to work out my distance. And the way which I'm going to do that is quite simply my data value take away my mean value. So now if I click enter, you can basically see it's 4.6. So 18 is 4.6 away from 13.4. In fact, let me make it a little bit bigger so you can see what's going on there. Okay. Now again, all I'm going to do is take this and drag it all the way down here. Okay, and I get something that looks like that. So I'm actually going to put this in a nice green. So I'm going to highlight all of that, and I'm going to put this in green. And what I want to now do is actually plot this on my graph over here. Okay, I want to plot this on my graph over here. So the way which I'm going to do this is actually using error bars. So I'm basically trying to say that that data point here, in fact, let me turn the highlighter on, that data point here is going to be 4.6 above the mean line. So I basically want to draw a line between that data point and where it should lie on the mean line. Okay, so the way which I'm going to do this is by adding error bars. So if I click my data points, you can see they've now been highlighted. And if I come over here to the plus arrow, you can see that there is an option for error bars. So now if I click my error bars, click tick, you can see these error bars have been added. Now the way which Excel adds an error bar by default is I think by 5% of whatever the data error is. Okay, so they basically look at the deviation of the data, and they add basically 5% each way, and that's how the error bars are calculated. I want to change that. So what I'm going to do is just click on the error bars, and I'm going to right click and then go format error bars, and it should bring something up over here. Now, because I want just basically a line between the data point and the mean value, I'm going to click minus. Okay, I'm going to click minus. And what they'll basically do is it'll just bring all of my error bars below my data points. Now, you notice that I have a bit of an issue because for data points above the mean line, they're all going to point downwards. Whereas you notice for this data point here, for example, I actually want the error bar to go upwards because it's upwards towards my mean line. That's fine because you notice for that data point there, it's negative anyway. Okay, so what I'm going to do is just click that. I'm going to go no cap because I don't want any caps on there. And I'm going to come down here to custom, and I'm going to specify a value. Okay, so the positive error value, I'm just going to click on this little arrow here, and I'm going to highlight this data here. Okay, and then when I'm ready, I'm going to click enter, and I'm going to do the same for the negative error value. So in that way, it doesn't matter whether I'm dealing with positive or negative error values. And now you can see that all of these data points are in the right direction because it's basically joining the data point to the mean line. Now I am just going to change a little bit of formatting with this data point. So I'm just going to right click on this. I'm going to go to outline. I'm going to change it to my green. And I'm also going to change it to a dotted line as well. So dashes, change it to a dotted line. And I might make it a little bit thicker as well. So let's go to 1.5 pints again. So basically what I've drawn in here with the green line is basically all of these distances here. And these distances just simply represent the distance between my data point and the mean value. Okay, so hopefully that makes sense. Now, if I want to find the average distance from the mean, surely it's just as simple as finding the averages of all of these distances. Okay, so I'm literally just looking at how far each data point is away from the mean line. That's what the green line represents. Basically look at these distances and average them. Okay, so I've got all these distances over here on my left-hand side. Surely it should just be a case of averaging that. But it's not. And I wonder if you can think why. Okay, so have a look. It's because I have some values above the mean line, but also some values below. So look at this data point here, for example. That's below the mean line. And you can notice, for example, that corresponds to a negative value. So if you think, if I'm going to take the average, surely it should just be a case of adding all these together. So by average, I mean mean. If I just add all these values together and divide by the number I've got, the issue with doing that is that I have some negative values. So in other words, some positive values and negative values are almost going to cancel each other out. And I'm no longer going to get a true average of what I want. So what I need to do instead is find a way of making all of these things positive. Well, if you think it's very, very easy to make all these things positive, all I need to do is square it, okay? Because squaring will always make something positive, regardless of whether it's positive or negative to start off with. So if I just take my distance and I square it, so if I say distance squared, okay, all I need to do is type equals, well, I want the value in that cell, so that distance, and I'm going to square it. So I'm going to go Shift 6 and then type squared, okay? Then hit enter. And that brings me back 21.6. Then all I need to do is just drag all of that down and it will give me the average distance, or the distances squared. So 4.6 squared will give me 21.16, 3.6 squared will give me that. You notice as well it doesn't matter whether it's negative, because of course negative times a negative will still be positive. That's exactly what I want. So if I work with squared distances, that means it's always positive, okay? Then what I can do is take the average of all of this data set, okay? So I'll take the average of the distance squared. Okay, so all I'm going to do, that's distance. So all I'm literally going to do is just say equals average of all of that lot. So I'm just taking the average of all of that lot, hit enter, and I get that. And again, I'm just going to lock those cells to make sure they don't change if I drag or drop it down. Okay, so now I get 18.6. That's the average of all of this data set squared. Okay, but of course that's not strictly speaking what I want, is it? Because of course, if I do that, that's just going to simply give me the average of the distance squared. Now I do give that a special name, okay? I call that the variance, okay? So the variance in this case is just going to be equal to whatever that is there. So before I if I just square it and take the average, so I square all of these distances, make them positive, take the average of that, I'm going to call that the variance, okay? Now variance is actually quite useful because it's able to determine whether there are any outliers in my data set. For example, if my variance is really, really big, that's going to be really big as well. So if there's a data point which lies, for example, 10 away from the mean line, if I square it, it's going to end up 100. Okay, so variance is a really good way of determining whether there are any averages or there are any outliers in the data set. Okay, now of course I'm not finished, because for standard deviation, so I'm going to call it SD for short, I'm going to need to take the square root of this value. Okay, because of course you notice that I squared it to make them all positive. Well, I need to undo that squaring. Okay, and I'm going to undo that squaring now just by going equals square root of that value there. And if I hit enter, that there is going to be my standard deviation. Okay, so 4.24735, that is my standard deviation. Okay, so standard deviation is really, really cool. Okay, it basically tells you the average distance from the mean. And there's a couple of different processes you need to do. Number one, you need to work out the mean of your data set. Then you need to work out the distances. Then you need to square those distances to make sure they're all positive, to make sure the positives and negatives aren't going to cancel each other out. Then you need to take the average of those square distances. That will give you the variance. Okay, so I will just highlight that as well. Okay, so that will basically give you the variance. Okay, but then to find the standard deviation, you need to undo that squaring, so you need to take the square root. Okay, so just be aware, standard deviation is really useful. If you have a big standard deviation, it means that all of your data points lie quite far away from the mean. If you have a small standard deviation, it means that all those data values are quite closely clustered together. It means you've got a low spread in your data set. Okay, and likewise, I've shown you a little bit of how you can use Excel and how you can kind of manipulate it to get a graph that looks something a little bit like that. Now, like I say, Excel is powerful. It can do really, really cool and amazing things, but do not be led to think that Excel is the be all and end all. Okay, be aware that Excel has limitations and do not abuse it. Okay, the one thing that you get, the one thing that you get all the time is people abusing Excel, thinking it should be used for something where it really shouldn't be. Okay, Excel is great for kind of visualizing data, using quick kind of summary things to do with data. But if you've got your raw data stored in Excel, do not edit it. Always do it somewhere else. Okay, and also just be aware that if possible, if you're going to really analyze data, you shouldn't be doing it in Excel anyway. You should be doing it in a completely separate program altogether. Okay. But hopefully that gives you a little bit of an idea of statistics, gives you a little bit of idea of summary statistics, and also a little bit of how to use Excel.